Cool. So thank you everyone for coming. So today we have the pleasure of having Michael Choi. So Michael is an assistant professor at National University of Singapore. He did his PhD in Cornell, and I think his research is quite interesting. It's actually like Markov process theory applied to like, a bunch of different areas, from information theory to like data science and so on. Yeah, that's something I find very interesting. And one thing I also noticed that I think it wasn't in the bio, but or maybe it was, I didn't notice it until I went through your papers. But you have like some decent amounts of work in information geometry, which is quite cool. Um, so after you, I'm pretty excited about the talk.
Yeah.
Yeah.
Thanks for the very kind introduction and thanks for the invitation to give a talk in this very interesting seminar. And yes, my talk today is going to be a bit about information geometry and in particular information projection. So my talk today is about improving the convergence of Markov chains using permutations and projections. So this is based on a paper of the same title that we have already posted on arXiv, which is a joint work with Max Hurt from UCL and also Youjia Wang from NUS, who is my PhD student. So much of my recent focus is on information theory of Markov chains, and in particular, what is now known as information projections and information geometry of Markov chains and MCMC algorithms. So after my talk today, I hope it is able to convince you to at least take some look on the paper. So this paper or this talk is hopefully interesting to you from at least the following two perspectives. First, we study new information projections of Markov chains, and this revealed to us previously unknown geometric structure in the space of transition matrices of Markov chains. And also, we use this geometric structure for good in the sense that we try to make use of this geometric information to help us design accelerated or improved MCMC samplers, leading to new algorithmic development in MCMC. So that is a high-level overview about this paper and also my talk today. So let's get started. So in this first section of my talk, I'm going to introduce the setting and introduce quite a few important notions and notations that I am going to repeatedly use in my talk later on today. So in the paper and also in my talk today, we just consider finite Markov chain. So there's a Markov chain on a finite state space, X. So it can be generalized to more general state space, but for simplicity, in the paper and also in my talk today, we just fix a finite state space setting. So we use this mathcal to be the set of transition matrices on the state space. And we use this mathcal S pi. So this S pi is the set of pi stationary transition matrices. So if you forgot about the stochastic process class is just the set of transition matrix P such that it satisfies pi p equals to pi for this given pi. So that's why this S bracket of pi here on the left-hand side. So as usual, in the Markov chain literature, we write P star to be the L2 pi adjoint of this transition matrix P. And some people also call this the time reversal of this P for P and S pi. So we will also use this notation today. So this L pi is the set of pi reversible transition matrices. So that is just the set of P such that it is self-adjoint, meaning that P star equals to P. So I use this L pi to denote the set of pi reversible transition matrices today. Okay, so the first important notions that I want you to keep in mind for the rest of my talk today is what we call isometric involution with respect to pi. So a matrix Q is said to be an isometric involution with respect to pi if it satisfies the following two criteria. So that means that it has to first, it has to satisfy Q squared equals to I. So this I is the identity matrix. So this Q squared equals to I is the first criteria. So the second criteria is that it is self-adjoint in the sense that Q star equals to Q. So if you give me a matrix capital Q that satisfies these two criteria, we set it as isometric involution with respect to pi. So some example of Q to keep in mind is are the following. So the first example of Q is just the identity matrix I. So you can see that I squared equals to I, and I star is also I. So this I the identity matrix is, of course, an isometric involution with respect to any pi. So another example of isometric involution is this plus or minus 2 pi minus I. So this capital pi is the transition matrix in which each row equals to small pi. So you can also show quite easily that this plus or minus 2 pi minus I also satisfy these two criteria. That means that plus or minus 2 pi minus I squared equals to I, and also the adjoint of this plus or minus 2 pi minus I equals to itself. So these are some good examples of Q to keep in mind. And I will write this I pi to be the set of isometric involution transition matrices with respect to pi.
Can I ask one question? Just
Yeah, sure.
maybe I'm jumping ahead. I don't know. But just in terms of terminology, like where is the isometry happening, or is it later at some projection level?
Where's the isometry? So it is embedded in this Q star equals to Q. So you can actually show that this two isometry being isometric and also being involution is equivalent to these two criteria in this context. Is Q squared equals to I. So that means it's an involution, and Q star equals to Q is actually implies that together Q squared equals I, it implies an isometry.
Okay, I guess I
So
forgot this.
it is a good question. So yeah, that's a good question. So now I would like to talk about this introduce and a generalized notion of self-adjointness. So if we have an isometric involution, capital Q, a pi stationary transition matrix capital L is said to be pi Q self-adjoint with and only with this L star equals to QLQ. So this is a generalized notion of self-adjointness in the sense that in a special case, again, we can always take Q to be the identity matrix. If we take Q equals to I, we actually recover this L pi I is actually L pi. So that means that the pi I self-adjoint notion is just the classical self-adjoint notion for transition matrix. So because if we take Q equals to I, it is just L star equals to L, but that is just the classical definition of self-adjoint transition matrix. And we will also write this L pi Q to be the set of pi Q self-adjoint transition matrices in my talk today. Okay, so the first important definition of today is this isometric involution matrix. So it turns out that it will play a key role in the rest of my talk today. That's the first important notion in this part. The second important notion that I'm going to introduce right now is what we call equiprobability permutation matrix with respect to pi. So I let this bold P, this bold and capital P to be the set of all permutations on the state space. And this psi be a permutation, and we write Q sub psi to be the induced permutation matrix. So now we define a set of what I call equiprobability permutations with respect to pi. So it's just this the set of psi such that it satisfies the following two criteria. So first of all, it is an involution as well, in the sense that if you apply this psi twice, if you apply this psi two times, so that's psi at psi of x, it maps back to itself. So it's an identity map. So psi applied twice at x, it gives it back to x. And also it is equiprobability in the sense that we require for all x, pi of x equals exactly to pi at psi x. So that's what I call equiprobability permutation with respect to pi, because for all x, it has to satisfy this equiprobability criteria. So so we can see that this capital, so I call this set of equiprobability permutation capital psi bracket of pi. So we can see that this set is actually non-empty for all pi because the identity permutation always belongs to this set.
Can I ask one question?
Yeah,
So
sure.
if pi has just all distinct values though, like like one, like I don't know, half
Then
only identity, right?
just the only identity. Yes, you're right.
Okay, cool.
It is a good point. So I come back to that point. I
Okay,
may
cool.
come back to that point
I'm just
later.
like trying to digest the definitions. Cool.
So now I would like to establish a link between these two notions that we just learned today. So the first notion that we learned today is this isometric involution. And just now on the previous slide, we introduced this equiprobability permutation. So now I'll try to link up these two notions together. So first of all, an isometric involution matrix, it may not be a transition matrix. So an example to keep in mind is this, again, this plus or minus 2 pi minus I. So they may not be a valid transition matrix. But then what is an isometric involution transition matrix? So it turns out that we can prove that, so this I pi intersect with L. So this left-hand side is just isometric involution transition matrix. And this right-hand side is just the set of equiprobability permutation matrices. So there's a Q psi, in which psi is in this capital psi bracket of pi. So the first takeaway message of today is that, so it turns out that on a finite state space, the set of the set of isometric involution transition matrix, there's this left-hand side, this I pi intersect with L, actually equals to the set of equiprobability permutation matrices with respect to pi. So there's this right-hand side. So that means that if we want to consider isometric involution transition matrix, we just need to consider equiprobability permutation matrix. So I will finish this section with a few interesting remarks. So first of all, why is this isometric involution notion important? So it turns out that many state-of-the-art non-reversible MCMC algorithms, so of course they are non-reversible with respect to pi. However, they actually satisfy some kind of generalized self-adjoint notion that we learned earlier today. That's what we call the pi q self-adjoint notion by suitably choosing q. And this actually motivates the study in this paper by Andrew and Livingstone, which is kind of like an important background for our paper and for my talk. And also later in my talk today, I'll review more connections between equiprobability permutations and a very famous MCMC sampler called equi-energy sampler by Choi and others. Okay, so that's the first part of my talk today. I fixed some notations, but most importantly, I want you to know that, the set of isometric involution transition matrix is just the set of equiprobability permutation matrix. That's the first takeaway. So now I would like to talk about information projections. In particular, I would like to project onto this pi q self-adjoint space. So before I talk about this projections, let us recall KL divergence between transition matrices of Markov chains. So for a given pi and two transition matrices, capital M and capital L, the KL divergence, the Kullback-Leibler divergence from L to M with respect to pi, so we write this as d pi sub KL from L to M is defined with this sum on the right-hand side. So as usual, to understand this sum on the right-hand side, there's a few standard conventions apply in this sum on the right-hand side. So this KL, this pi, it may not be the stationary distribution of L or M, but however, with M is pi stationary, this definition of the KL divergence from L to M is actually the KL divergence rate from L to M. But it's just some background about this KL divergence between transition matrices. So at a conference in MCMC called MCQMC in the past summer, so that is, I think in August of 2024, that was actually in Waterloo, at University of Waterloo. Max Hurt raised to me the following question. So if we have a pi stationary transition matrix capital P, and Q be an isometric involution transition matrix with respect to pi, so what can be a projection of P onto the set of pi Q self-adjoint transition matrix, so that we denote by L pi comma Q under the KL divergence? So one way to formulate this question mathematically is to solve the following minimization problem. So we're minimizing this pi-weighted KL divergence that we just introduced from M to P, where M belongs to this set of pi cube self-adjoint transition matrix. So we would like to solve or to tackle this minimization problem. So it turns out that this minimization problem is minimizer is actually this P bar Q that I now introduce. So this P bar Q, we define this on the right-hand side to be just 1/2 times this P plus Q, P star Q. And I use this notation of P bar because you can understand this as an average. So that's why I use this notation of P bar. So it's an average between P and Q, P star Q. So that's why I use this notation of P bar on the left-hand side. And also this is a function of Q, because this Q, you can understand this as a parameter or as an input to this average. So that's why on the left-hand side, I write this notation as P bar bracket of Q. So in the Markov chain literature, it's also known as a mixture of permuted Markov chains. So because you can see that this is an equal probability mixture in the sense that to simulate one step of P bar Q, you just flip a fair coin with probability 1/2. You use P with another probability 1/2. You use Q, P star Q. So that's why in the literature, this P bar bracket of Q is known as a mixture of permuted Markov chains. So it turns out that we actually establish what we call a Pythagorean identity in the sense that you have this theorem 3 as shown on the slides right now. And in particular, this Pythagorean identity implies that the unique minimizer to this minimization problem is actually given by P bar Q. So this P bar Q is again this mixture of permuted Markov chain that we learned on the previous slide. So the second takeaway message of my talk today is that this P bar Q is actually the unique information projection of this given transition matrix capital P onto the set of pi Q self-adjoint transition matrices.
Can I ask one
Yeah, sure.
So I have a question, but is this purely of actual interest, but in a slightly more generalized setting? Do you think your proof would work for like other, I guess, like other divergences that are sufficiently nice? Specifically, there's
Yeah. It will work. So okay. So I have thought about that question, and actually that question is also raised to me by one of the reviewer of this
I'm not, it's not me.
of the paper. I've already thought about this question. In fact, for F divergences, you can actually generalize it to, but then the corresponding information projection may not be this P bar Q.
Yeah.
So it turns out that there's some advantage in considering KL divergence in the sense that the information projection is given by this P bar Q, in which you can easily simulate this P bar Q. But for other F divergences, such as, let's say the reverse KL divergence, which is a member of this F divergence family, the reverse KL divergence, the information projection in this structure is actually given by what is known as exponential reversibilization, which is much harder to simulate than this P bar Q. But that's a very good question. So for F divergence, you can actually show that there's also, you can actually prove that there's also a unique information projection, but whether that information projection can be readily simulatable or can be readily be applied to MCMC is another story.
Sure.
However, for KL divergence, the resulting information projection is quite easily simulated in the sense that this P bar Q, if you look at this definition on this slide, it's just, again, you flip a coin with probability 1/2, you use P, another probability 1/2, you use Q, P star Q. So that is quite easy to be simulated. But on the other hand, if you end up getting more complicated information projection on the more other choices of information divergence, such as F divergence, the resulting information projection may not be directly be able to be simulated. So, but yeah, it's a good question.
I only ask if you're interested because specifically, have you ever heard of like the E gamma divergence?
Yeah, I heard about this. Yes.
Yes. So this is very useful in differential privacy, but it's also very simple. It's like it has simple like F function. It's like a ReLU kind of thing. Yeah, so I'm just curious because then this would have a lot of applications in differential privacy directly.
I
Um,
see. I see.
yeah,
Yeah, I don't know about this. Yeah, I don't know about this application in differential privacy, but I will look into that then.
yeah, it seems pretty cool. Thank you, thank you.
Okay. Okay, as usual, I will conclude with some remarks for this section. So, in case you're not familiar with the field of information geometry, one cornerstone result in this area is this type of Pythagorean identities that we establish. So, for example, you can consult the work of Amari or my collaborator Wolfer and Watanabe. And also, in the paper, we also established Pythagorean identity under squared-Frobenius norm. So that is this norm sub F is the matrix Frobenius norm. So more generally, I think the result can be generalized to some Bragman divergences. But I mean, I didn't pursue this direction in the paper. And also I didn't really, I mean, I just read this on my slide. I mean, I didn't really think about this deeply, but I think the result and the proof can be generalized to some Bragman divergences. Okay. So in the next part, I'm going to develop what is known as comparison theory in Markov chain literature. So I'm going to compare the convergence speed of some Markov chain samplers. So in the context of MCMC, so samplers such as Metropolis-Hastings or Gibbs sampling are frequently used to approximately sample from pi. So this pi is a given target distribution. So now in the context of this paper and also in this talk, we actually now have quite a few Markov chain to choose from now. So again, we start with an ergodic pi stationary P and also an isometric involution transition matrix capital Q. So now, so let's say we can have a Markov chain that use P or use QP or use PQ or use QPQ or using this P bar bracket of Q that we just introduced, this which is given by this 1/2 times P plus QP star Q. Or more generally, we can consider a mixture in which it is this alpha P plus 1 minus alpha Q P star Q. So this alpha is any real number, is any number from 0 to 1. So the point is that now we have quite a few Markov chain sampler that we can choose from. And ideally, I would like to pick the fastest one under some suitable metrics. So I would like, so all this transition matrix, you can prove that they converge to this given target distribution pi. And ideally, I would like to compare the convergence speed of all these competing Markov chain samplers and pick the fastest one if possible. So it turns out that and the most commonly used metrics in the Markov chain literature and suitable assumptions, this P bar bracket of Q is actually preferred over the others. So in particular, this convergence metrics include the following list of metrics, like the SLAM, that is the second largest eigenvalue in modulus, the spectral gap, the Dobershin coefficient, Cavendish constant, asymptotic variance. And all these are very common metrics that people study in the MCMC literature. So I don't have time to go through the proof, but then you can consult our paper to see how we showed this P bar Q is actually have a better convergence metrics than the other competing samplers. So the third takeaway message in this part is that P bar bracket of Q is actually a preferred sampler of pi compared with the original P or other competing transition matrix. So based on the most commonly used metrics.
Can I just ask one tiny question, just to like, um, yeah, to understand. So this is So P bar Q is, I guess, better for all these metrics, I guess,
Yeah, yeah.
or
But at the
interesting.
same time, there's at each step there may be additional computational costs, but
Yeah,
that may be so because we just compare this P with this P bar Q. So
mm,
at P bar Q, you need to first flip a coin. With 1/2, you use P, but with another 1/2, you first apply this equiprobability permutation capital Q, and then you apply P star, and then you apply Q. So that using P bar Q, on one hand, it can give us better convergence metric, but on the other hand, it also comes along with additional computational costs for each step. But hopefully that additional cost is kind of negligible or kind of like minimal in some sense. So yeah, I will talk more about this in my talk later today. It is a good question. Okay. So the next part, I am going to talk about alternating projections to combine Qs. So the setting is as follows. So let M be a positive integer, and suppose we have a sequence of isometric involution transition matrices that we call Q0, Q1, Q2, up till Qn minus 1. So we have a sequence. So now we not only have one Q, but we have a sequence of Qi. So Q0, Q1, Q2, Q3, up till Qn minus 1. I would like to develop a way for me to combine this Qi to further improve the convergence to equilibrium. Then a natural idea in this context is alternating projections. So how does that work? So again, we start with a given Markov chain sampler described by this transition matrix, capital P. So we first project this P onto the space of L pi Q0 to obtain R1. So again, this R1 is just defined by this P bar bracket Q sub 0. And then we further put, making use of this R1, we further project this R1 onto the space of L pi Q1, that is the second Q, that is Q1, to obtain R2. So mathematically, R2 is just R1 bar, bracket of Q1. So we repeat this alternating projection construction. So the next step, we project R2 onto the space L pi Q2 to obtain R3, and R3 is defined to be this R2 bar Q2. So we proceed iteratively, and projection order is deterministic in a cycle in the order of Q0, Q1, Q2 up to Qn minus 1, and then you go back to Q0, Q1 up to Qn minus 1, and you go back to Q0. So precisely, you can define this recursion in this formula. So this Qn is just, sorry, this Rn, sorry, not Qn, but Rn. Rn is defined to be this Rn minus 1 bar at Qn minus 1 mod m, with the initial condition being R0 equals to P. So this is a diagram. So in case you're a bit confused by the notation so far, so this is just a visualization of the alternating projection when we have two Qs. So that is when we have Q0 and Q1. So that's m equals to 1. So again, so let's say we start with this R0. So that is P. So in the first projection, we project this R0, or we project this P onto L pi Q0 to obtain this R1. And with this R1, we further project this to the space L pi Q1 to obtain R2. And we further project this R2 back to L pi Q0 to obtain R3. And then from R3, we obtain R4, and then R5, and R6, and R7, and so on and so on. So that is a simple visualization when we only have, when we're in the case of m equals to 1. So that means we just have two permutation matrix, Q0 and Q1. So, okay, so so first of all, what is the benefit of doing this? So the main benefit is that at each step, the project transition matrix is actually improved compared to the previous unprojected matrix in view of the results in previous section. So in other words, we try to make use of this geometric structure to give us a better Markov chain sampler through alternating projections. So now, let me denote this intersection of this space to be this capital epsilon. So there's this intersection of L pi qk, and you intersect k from 0 to m minus 1. So that is just the intersection of all this pi qk self-adjoint spaces. So this L pi q0 intersect with L pi q1 up to L pi qm minus 1. This is given by this capital epsilon. So now I use this notation R sub infinity to be the projection of P onto this intersection, onto this capital epsilon. So that is mathematically given by this mean of this K of divergence from N to P, and N is a member of this intersection, so N is in this capital epsilon. So it can be shown this R infinity is unique. And using the theory of alternating projections, you can actually prove that this Rn converge to this intersection R infinity element-wise. So if you go back to this first simple case, so you have two. So you imagine this L pi Q0 and this L pi Q1. The intersection is given by this shaded region at the bottom. And if you directly project this P onto this intersection, you will get this R infinity. And you can prove that this Rn, the sequence of alternating projections, actually converge to this R infinity using existing theory of alternating projections. So precisely, you can prove the following limit exists in the sense of pointwise convergence or in total variation. So this limit of Rn, and as n goes to infinity equals to R infinity. And furthermore, this R infinity is belongs to this space. And another very intriguing property that I'm going to mention later on in my talk as well is this, what I call trace preserving property. So that is the trace of R infinity actually equals to the initial trace. So again, we start with an initial Markov chain sampler that is described by this capital P. So this, it turns out that you can prove that this projection is trace preserving in the sense that the trace of Rn and also the trace of R infinity, they're all equals to the initial trace, to this trace of P. So the fourth takeaway message of my talk today is that if possible, we can consider to use the alternating projections Rn, or more generally this limit R infinity if possible. The reason for doing so is because you can, as what we have seen earlier in my talk today, all these alternating projections or its limit are going to have better convergence metrics than the initial P. So they cannot be worse off in terms of convergence speed to pi than the original P. But on the other hand, as I've mentioned earlier in my talk today as well, using these alternating projections may also incur additional computational costs than the original P. So there's a trade-off to keep in mind, because so a few remarks here. So I'm not the first one to consider alternating projections in the context of MCMC. In fact, they have already been used, or this concept have been used in a study of Gibbs sampler in this paper by Percy Diaconis and others, and also more recently in a paper by Qianqing. So assume that we can simulate the original transition matrix capital P. Can we simulate the trajectories of the Markov chain with transition matrix Rn? And in the paper, we actually devised a recursive simulation procedure to do so. And another natural question to ask is that, what is the rate of convergence of Rn towards R infinity? So it turns out that it depends on the angle between suitable subspaces. So I don't have time to talk about this underlying theory, but I think it's quite beautiful. So you can consider the paper with, because this angle between subspaces, it actually quantified the rate of convergence of Rn towards R infinity. And if you go back to my earlier graph, you can actually show that the angle, if you have two subspace in this case, is actually given by this angle. If you follow my mouse cursor, it's actually given by this angle in the case of two subspaces. So, and more generally, you can, if we have like more than two subspaces, you can define this angle suitably, and that angle will actually quantify the rate of convergence of Rn towards R infinity. Okay. The next part, I'm going to talk about the maximum speed limit of this projection procedure. So that means that how fast can we go with this projection? So first of all, I would like to talk about the maximum speed limit, but in the school zone of Singapore. So this is what we call speed limit, right? So in the school zone of Singapore, you cannot drive. I mean, the driving speed cannot exceed 40. But in the context of projection sampler, so what is the maximum speed that we can go? So the maximum speed ideally is just capital pi. So this capital pi is just the matrix in which each row is small pi. So I would like to investigate situations in which we have Rn equals to capital pi. So that is a very ideal situation because now with that can be achieved, there's actually an exact sampler by simulating directly Rn. And this is unlike most MCMC samplers, which are approximate samples of pi. So the first result that we proved is that, so with Rn equals to capital pi for some positive integer n union positive infinity, you can show that then a necessary condition is that the trace of p has to equals to 1. So that implies that for pi reversible positive definite transition matrices, for however permutation matrix that you choose, the sequence of alternating projections cannot achieve capital pi because trace of p is strictly bigger than 1. And another very interesting necessary condition is to analyze through what is known as Sylvester equation. So I don't have time to talk about Sylvester equation and its theory today, but in a nutshell, we just apply this Sylvester equation theory in this context to obtain the following corollary 7. So if we write lambda bracket of P to be the set of eigenvalues of this matrix P, a direct application of Sylvester's theory give us the following result. So if we are with P bar bracket of Q equals to capital pi, then P and negative P star, they have to share at least one common eigenvalue. So this gives us some spectral or some eigenvalue characterizations of when will we achieve this P bar bracket of Q equals to capital pi. And it turns out that this trace condition that I mentioned earlier is actually necessary and sufficient to achieve R infinity equals to capital pi under some additional assumptions. So, okay, so the additional assumptions are the following. So if we assume this pi to be the discrete uniform distribution on a state space and P be a symmetric and doubly stochastic transition matrix, then under the above assumptions and suitable choices of the equiprobability permutation matrices, we can actually prove that R infinity equals to capital pi with and only with the trace of P equals to 1. So the takeaway message of this part is that we should consider transforming the transition matrix so that a satisfied trace of P equals to 1. So depending on P, so it may not necessarily leads to Rn equals to capital pi, but at least it seems to make the matrix chain better conditioned. So the second last section of my talk today, I would like to talk about some tuning strategies of Q. So in my talk today so far, so you should be able to learn that this isometric involution transition matrix can be understood as a parameter to this sampler, and the improvement depending on how you choose or how you tune this parameter capital Q. So for example, the choice of Q equals to I is always feasible, but it leads to no improvement because P bar bracket of I equals to P. So on the other hand, we have seen in earlier sections of my talk today that depending on P, it may be possible to achieve Rn equals to capital pi or R infinity equals to capital pi with suitable choices of Qs. So the first strategy is to tune this parameter Q using optimization and Markov chain assignment problems. So a natural strategy is to find Q that minimize the discrepancy between P bar bracket Q and capital pi. So that means that we are interested in the following minimization problem. So we are minimizing over Q in the set of equiprobability permutation matrix, or equivalently the isometric involution transition matrix. So we are minimizing over Q of this K of divergence. This is the K of divergence from capital pi to P bar bracket of Q. So we want to minimize this. However, that may not be solved in realistic time frame in practice, because this capital pi in MCMC, it usually involves normalization constant that is non-trackable. So this optimization problem may not be able to be solved in realistic time frame in practice. However, we can actually make use of the Pythagorean identity to transfer this problem into an equivalent maximization problem. So you can actually use the Pythagorean identity that we learned earlier today to transform the earlier minimization problem into this maximization problem. So now we are maximizing the K of divergence of this P bar Q psi to capital P. And we are choosing this psi to belong to the equiprobability permutation with respect to pi. So this rightmost maximization problem can be understood as a Markov chain assignment problem constrained to choosing equiprobability permutation within this set of psi, capital psi of pi. So in general, assignment problem can be solved in polynomial time in the size of the state space. But in the context of MCMC, this again may be infeasible in practice, because for many models of interest in MCMC, such as Ising model or the Potts model, the state space can be exponentially large.
Do you mind if I ask a question? I was trying to hold it to the very end, but
Sure.
I think it could be maybe it's a good time to ask it. Yeah. So this also relates to what you said earlier about computational like complexity, I guess, you know?
Yeah.
Um, yeah. So we always know that there exists. Okay, how do I say this? Yeah. Would it make sense to instead of maximizing over all like all these matrices, like the isometric convolutions, so on? Would it make sense to consider ones that are like sufficiently sparse? For example, we always know you have like I don't know, I forget like the cardinality of X on the diagonal, but you know, or like some low rank or like but anyway, some sparse subset or
Yeah,
something.
I think it's a very good question. I didn't think about this. But yes, I think that if you consider only like sparse Q, that may be able to speed up the optimization problem. But
Yeah,
it's a very good question.
yeah, because then the
I
state
did
space is similar to like I mean, you can potentially even constrain the complexity to be almost like about order of like P basically like the difficulty is simulated. So I don't know.
Okay. Okay. Yeah, thanks for
What
the
do you say?
suggestion. Okay. So the earlier considerations can be further generalized to consider multidimensional assignment problems. So now, we are not just optimizing one single Q. So early on, we just have one single permutation or one single capital Q. So now so let's say we have MQ, so given by this Q psi 0, Q psi 1 up to Q psi M minus 1. So that is, again, we try to minimize this. So this RL is the alternating projections that we learned earlier. And again, you can transfer this minimization problem to a maximization problem using the Pythagorean identity that I developed earlier. And this becomes a multidimensional assignment problems, because now we're not just considering one single permutation. We now have M permutations to maximize with respect to, and in general, it is MP hard to solve. However, they're useful heuristic in practice to solve multidimensional assignment problem. So see the paper for more discussions. So this is the first strategy, but this strategy can be quite computationally intensive in the sense that it requires you to hopefully find an optimal Q by solving some kind of maximization or minimization problems. The second strategy that we develop in the paper is an adaptive strategy. So we try to tune Q adaptively in a single run. So what do we mean by that? So let's say the target distribution is the Gibbs distribution. So that is a very common target distribution in MCMC. So this is given by this Gibbs distribution and inverse temperature beta. And this capital H is what we call the target energy function. And this is capital C sub beta is the normalization constant of this Gibbs distribution. So it turns out that equiprobability is the same as equienergy, meaning that you can easily show that pi x equal to pi y with an only of hx equals to hy. So that means that equiprobability permutation is the same as equienergy permutation. So the second strategy is an adaptive strategy. So that means that we start our initial Q to be the identity matrix, and we learn the equiprobability or the equienergy permutation adaptively on the fly as the algorithm progresses. So the third strategy is that you first run an exploration chain, such as the proposal chain in Metropolis-Hastings or the Metropolis-Hastings chain at high temperature. And so you run some exploration chain, let's say for k times, and each time you learn an equienergy permutation. So we call this equienergy permutation Qn, n from 0 to k. Oops, sorry. So hopes it should be 1 to k because we just learned it k times. And then you combine these permutation matrices using alternating projections. And this is inspired by the equienergy sampler by Choi and others. So in this strategy, you first run an exploration chain for k times, and then each time you learn a permutation matrix, and then you combine this permutation matrix using the alternating projections. Okay, animation time. So I'm going to show you guys an animation, which is about this Ising model on the line. So which is a very common statistical physics model. So we will see that the adaptive projection sampler is able to hop between the two modes. So in this model, the Gibbs distribution has two modes. So this is given by the all black and the all white configuration. And we compare this adaptive projection sampler with the standard Metropolis-Hastings. And you will see in the animation that the standard Metropolis-Hastings struggles to transverse between the two modes. So the animation credit and computational assistance is from my student Youjia Wang. So now I'm going to the animation. Can you guys see the animation? I haven't clicked the start button. Okay, good. So now I'm going to click play in the animation. So this is the standard MH. This is the adaptive projection sampler. So the red line here is what we call the adaptive projection sampler, and this is the plot below is the magnetization. So that's just the average of the coordinates. So you see that the red line is able to hop between across the magnetization, and the blue line will exhibit what is known as diffusive behavior. So you will see the blue line is not able to make such a large jump because it is just a Metropolis-Hastings sampler. But however, the red line is able to make use of the permutation to hop between the two modes. So the two modes are the all black and all white configuration, and that means the magnetization is exactly equals to 1 and exactly equals to -1. So you will see that the red line is able to make very long jumps or to make use of the permutations to jump between configurations, and that the blue line or the standard MH struggles because the blue line is a standard Metropolis-Hastings, so it exhibits what is known as the diffusive behavior in the MC literature. So you can see that the trajectories of this blue line of magnetization looks like a diffusion, but on the other hand, the red line can exhibit jumps like here or here. So you will see that this projection sampler can in this very toy model, in this icing model on the line, can indeed allows the sampler to hop between the two modes. So the two modes is given by this +1 and -1 in magnetization. All right, so there's enough of the animation for today. So it is just to illustrate that this projection sampler can indeed give us some practical acceleration benefit in the context of MCMC. So some final messages and some outlook about this paper. So hopefully after my talk today, I've convinced you that this paper or this talk presents a new technique of improving the convergence of Markov chains using permutations and projections. And in a very broad sense, this technique can be understood as a preconditioning technique to improve the mixing of Markov chain. And I really like this idea, or I find it intriguing, because we are using a lot of mathematical ideas for good in the context of MCMC. So in my talk today, you see ideas from information projections, alternating projections, Sylvester equations, assignment problems, all naturally come together to help us to design accelerated or improved MCMC samplers. So some ideas for future work. So one possible idea is to extend the methodology to more general state space. So in my talk today, we only consider finite state space, but I believe most of the results can be carried over to general state space and also processes such as diffusion process. And also, I'm also interested to design better samplers for problems in TCS, because a lot of problems in TCS are people actually run MCMC samplers to solve some problems in TCS. So I'm also interested in designing improved samplers for problems in these directions. And another possible direction is implications for sequential Monte Carlo, SMC. So you have n particles, and those particles may interact in this kind of sequential Monte Carlo samplers. So can we make use of this projection technique to further improve SMC? So these are some very open questions. I just write it out here. So in case you're interested in pursuing this direction, you're more than welcome to join me in this direction if you're interested. All right. So that's all for my talk today. Thank you very much for joining me today, and I welcome any question from you.
Thank you very much. It's a very interesting talk and very engaging also. I'll ask, does anyone have any questions in the audience? I definitely asked a lot of questions throughout. Anyone? Maybe shy? No. Yeah, honestly, I asked like most of my questions throughout. If I have any more, maybe I'll send you an email. But yeah, but it's extremely interesting. Oh wait, I do have one last one. I'm gonna try to remember what it
Oh, yeah,
was.
sure.
Yeah,
Sure.
I was like, what was it? Yeah, so I think you kind of essentially asked it, but maybe, I've only had one coffee, so maybe the question is silly. Um, but is there a way to like kind of randomly sample in a good heuristic way, like just from like one draw, a good cue, or whatever this means, instead of like optimizing it?
So we actually have a theoretical result in the paper that say that we consider random projection. So that means that we consider a randomly chosen Q
Mm,
um,
mm,
from the set of all Qs on the state
yeah,
space. So we can show in that theoretical example, even if we just randomly choose a Q, it still lead us to substantial improvement in mixing times. But that is again a very special case and is under some strong assumptions. So
okay.
I don't know about the fully general case, but then under some suitable assumptions that are quite strong, we prove that under random projections in the sense that you choose this isometric involution transition matrix capital Q randomly from a suitable set, it can still lead to substantial improvement in mixing times, even if you just choose this Q randomly.
Can I ask you
But it's
one
a very
question?
good question.
Just like a follow-up question then. So yeah, so I guess I have a question. So what do you mean by random? Like, because for example, like there's like random, like classical random projections is like random Gaussian ones, but then there's like, for example, smart random projections where you have like, Bernoulli. Oh, sorry. I think we lost. I think I
No, no,
disappeared.
I'm still here. I'm still here.
Oh, okay. Yeah, sorry, sorry. Yeah, so for example, can you like like how is this matrix drawn basically? Like, can you enforce some kind of sparsity at the draw?
Yeah, I think this is a very good question. I didn't think about sparsity at all in this paper so far. So
Yeah,
yeah,
well,
I
this
don't
is very
know.
interesting. Okay, cool,
Yeah.
cool. I mean, it's very interesting talking. So we're gonna have
Thank you. Thank you so much.
to. Okay, so if there's
I'm
any,
glad that you enjoyed it. It relates to the information geometry. So that's what
yeah,
so it try to use a bit of information geometry to guide us in designing MCMC samplers.
yeah, that's pretty cool. Any other questions? Last chance. Okay, cool. In that case, I guess to you, good night, I guess, or a good
Yeah,
evening. I don't know.
I'm going to
And
take a I'm going to take a good rest tonight.